last few modules, we have done perturbation theory, and in perturbation theory, we talked about degenerate perturbation theory and non-degenerate perturbation theory, and both were time independent perturbation theory. Okay, and you have seen that both the theories are different. So if you want to calculate the correction to energy and correction to wave functions for a degenerate system, you should use degenerate perturbation theory. And if you want to calculate the first order or second order correction to energy and first order correction to wave functions, then you should calculate it by non-degenerate perturbation theory. We did problems also of non-degenerate perturbation theory, because the problems from this part of the theory comes most often in exams. Okay, so we did not do perturbation problems based on degenerate perturbation theory. If I get the time, I will do that again in the next or the last module. But before that, let me finish the time dependent perturbation. For the time dependent perturbation, it's very important perturbation theory, because from this what we can get is the selection rules, which is very important for spectroscopy. Okay, and this selection rule depends upon transition moment integral. And when I was doing your particle in a one-dimensional box, I talked about that transition between n is equal to 1, n is equal to 2, n is equal to 3 energy levels in the particle in one-dimensional box can take place, but provided that delta n is equal to plus minus 2. So this was the selection rule, and we did it qualitatively. I gave you one principle, that if the transition moment integral is non-zero, then the transition is feasible, and if it is zero, transition is not feasible. Okay. Today you will see that why this principle we used in the initial few modules when I talked about particle in a one-dimensional box. Okay. So time dependent perturbation means what we have to use is time dependent Schrodinger wave equation. We throughout this course from the very beginning, we have used time independent Schrodinger wave equation. In none of the module I have used time dependent Schrodinger wave equation, but in this module, in this theory, we will use this particular example. H psi is equal to H psi, which psi is dependent on x and t, is IH cross del psi x t by divided by del t. This equation I wrote once earlier also when I was talking about postulates of quantum mechanics. That the last postulate is that the time dependent Schrodinger wave equation is H psi is equal to IH cross del psi by del t. That's all. That thereafter we never used it. Now today we are going to use it. Okay. So what does it mean? That if your psi here the psi is a function of two variables, x coordinate and time t. So x coordinate, certainly I have taken only one coordinate, it could be other two, or psi rt also you can write. Okay. So if you put this value of psi xt into the Schrodinger wave equation, what do you get? You get h prime psi x ft is equal to IH cross del psi x by ft into del t. Okay. So, and if you do a little calculations, what do you find is that 1 over psi x, here you are differentiating with respect to time. So psi x you can bring outside, and that psi x I have brought here on the left hand side, and this ft can come on the right hand side, and then you have del ft by del t. If you look at this equation, the last one, this part is x dependent and this part is time dependent. Again, the same thing which we have done many times, separation of variables. Okay. So LHS is x dependent and RHS is t dependent. So both sides must be equal to a constant, say E. So if I equate it to E, then the two equations you can write, and one equation will be h psi x is equal to E psi x. So this is the normal relationship which we have used throughout this module, throughout this course. The Schrodinger wave equation, time independent Schrodinger wave equation we get from the left hand side, and from the right hand side what you get is IH cross ft del ft by del t is equal to E, and so del ft by del t you can write as minus IH divided by h cross E into ft. Okay. So this equation can be integrated, and if you integrate this, then ft you can write as exponential minus e t divided by h cross. So this is important. So the time dependent part of the function, of the wave function, can be written as exponential minus I e t divided by h cross. Okay. So this part is known to you already. H psi is equal to E psi, you have written time and again. And this, the time dependent part is an exponential part and it is an imaginary part, minus I e t divided by h cross. Okay. So if we use h nu is equal to h cross omega, then what do you get? You can write this as ft is equal to minus I omega t. Okay. We have not used till now anything about the perturbation. We are just talking about the time dependent Schrodinger wave equation, nothing else. Okay. So this you get ft and what does it means? It means that ft oscillates harmonically in time. The equation is exponential minus I omega t. So this is the harmonic oscillation, means it is the characteristic of the wave functions, the characteristic of the wave, okay, or wave equation. So we have this equation that psi xt could be, now psi, combine both these, so psi xt could be psi dependent on x and this part is t part, time dependent part and x dependent part. So the total function is multiple of both these functions, okay, that you know. And so we can write in terms of r, if the r is the coordinate, then you can, in terms of r also you can write for any function which is dependent on coordinate and time, could be written as psi n r. This is r dependent part, exponential minus I e t divided by h cross is the time dependent part. Okay. Once we have this one, then we can use this equation into the perturbation theory or the first order perturbation theory. Okay. So now if a molecule is interacting with an electromagnetic radiation, what will happen? In a spectroscopy, what happens? You expose your molecule to electromagnetic radiation, and this electromagnetic radiations, the electric field is given as E naught cos 2 pi nu t, where nu is the frequency and E naught is the electric field vector. This is the normal electromagnetic equations. So if mu is the dipole moment of the molecule, then the Hamiltonian operator of this interaction could be written as this one. This is perturbation, Hamiltonian operator. Now a departure from the previous modules where I have written H prime as the perturbation. Now here I have written H1, so don't get confused with that one. So this perturbation is minus E mod of E. So it will be minus E naught cos 2 pi nu t, and then we should solve h psi is equal to I h cross del psi by del t. This equation we have to solve. Perturbation is now known to you. Okay. So what is the unperturbed system Hamiltonian? System of the perturbed Hamiltonian, then it is unperturbed Hamiltonian, that is perturbation, so that you know. So a perturbed Hamiltonian could be written as h naught minus mu E naught cos 2 pi nu t. Okay. Once we have this one, Hamiltonian operator of the isolated molecule, and H prime will cause what? Can cause transition from one state to another state. Because see, H prime or H1 which I have written is the dipole moment, includes the dipole moment operator, okay, and where mu is the dipole moment, okay. So this will result into the transition of the system from one state to another state. We will see later on. In the absence of time dependent perturbation, H naught psi is equal to I h cross del psi by del t, okay. Now we will consider a two-state system. If you have two-state system denoted as psi 1 and psi 2, okay, we are omitting the possibility that there are many different energy levels. We are just sticking to two-state system, one designated as psi 1, another designated as psi 2, corresponding to different energies E1 and E2, obviously. So psi 1 t, what you can write? Psi 1 t can be written as, because it is a psi 1 exponential minus I E1 TH. So this psi 1 without any variable is actually coordinate dependent, and this part is time dependent. So that you should always remember. Then psi 2 also you can write in the same way, psi 2 exponential minus I E2 T H cross. Okay. Now we assume that initially the system is in a state 1. We allow perturbation to begin at time t is equal to 0. Now here is a perturbation which is because of the electromagnetic radiation which is falling on the system. Okay, and this electromagnetic radiation, when it falls on the system, it causes perturbation because it interacts with the system, and this interaction is because of the dipole moment of the system. Okay, so that perturbation we saw. Now we say that the system has two energy levels, and initially the system is in psi 1 state, psi 2 state is empty. Okay, so if the system is, if your molecule is in the lower energy state, psi 1 state, then the moment the energy falls, the perturbation begins, and so there will be a time lag between the a time of a start of the perturbation. So it is time dependent. So time of start of the perturbation is the moment when the electromagnetic radiation falls on the system. So that's what we have written. We allow perturbation to begin at time t is equal to 0. Okay, and assume that psi t is a combination of psi 1 t and psi 2 t with coefficient that depends on time. Now the moment perturbation happens, then though the system is in psi 1 t, but the total wave functions we can take as a linear combination of the two wave functions, because these are the solutions of the system, okay, with different coefficients. So we write the psi t as a combination of psi 1 t and psi 2 t with the coefficients a1 and a2. Okay, if we take this coefficients a1 and a2, which is then what happens, a linear combination of AI star. AI is the probability that the system is in the ith state. If you want to calculate the probability that whether the system is in psi 1 state or psi 2 state, then what you need to do, you need to square these wave functions. Okay, so if you want to know the probability of first state, what you do a1 into a1 star. A star I am saying because everywhere you see the time dependency is is a complex function, an imaginary function, so complex conjugate you will take. Okay, and if you want to find out the probability in A2 state, how much of the molecule has migrated from the lower energy state to upper energy state, then it will be A2 and multiplied by A2 star. Okay, that will give you the probability. This we will use. Now again the same relationship which we have used, and here we put the value of psi as a linear combination. So this psi is now a1 t psi 1 t plus a2 t psi 2 t, and then I h cross del by del t, and again psi is a1 t psi 1 t plus a2 t psi 2 t. Okay, if you solve this equation, then what do you get? This h naught t you will multiply, and what you will get? You will get a1 t h naught psi 1 t plus a2 t h naught psi 2 t plus a1 t h1 prime psi 1 t plus a2 t h1 psi 2 t. From where we get this h naught value? Because this h will be a summation of both these I have given you earlier. Hamiltonian which you have to use is for the perturbed system, and in perturbed system the Hamiltonian will be, where I have written, yeah, this one, Hamiltonian h naught plus h1. Okay, so this Hamiltonian is actually, yeah, this h1 also will be part of this Hamiltonian. H naught, this h naught is now h, and for h you write h will be equal to h naught plus h1. So you get these equations, a1 t h1 psi 1 t plus a2 t h1 psi 2 t. Okay, so this is your left hand side. On the right hand side again you have to differentiate. So the first term will be I h cross del by del t del psi 1 t by del t, and then the second term will be I h cross a2 t del by del t psi 2 t, and then plus IH cross psi 1 t del A1 t by del t and IH cross psi 2 t del A2 t by. So all these four terms are separately differentiated. Okay, and using this one, H naught psi 1 t is equal to H naught psi 1 t is actually has both the part psi 1 into exponential minus I E1 t divided by h cross. This is very important because this tells you the coordinate dependence, this tells you the time dependence. So this I have replaced psi 1 t, you can replace by psi 1 exponential minus I E1 th, or what you can write is H naught psi 1 you can bring here, and H naught psi 1 will be equal to E1 psi 1. So it will be E1 psi 1 into exponential minus I E1 t h cross. Okay, so no issue, we can do this one. We can cancel first two terms on both sides of the equation. Okay, A1 t H1 psi 1 t, if you use this equation, then we can cancel both first two terms. This term will go, this term will go, this term will go, this term will go. So what remains? What remains is A1 t H1 psi 1 t, A2 t H1 psi 2 t, and plus IH cross psi 1 t del by del t of A1 t and IH cross psi 2 t del. So two terms on the left hand side and two terms on the right hand side remains. These four terms go. Okay, you can see if you equate this one, you will get this one. Okay, so we can cancel first two terms on both sides of the equation. We have this equation. Now from this equation, multiply by this equation by psi 2 star and integrate over spatial coordinates. Integrate over spatial coordinates. So what will you get? If you multiply by psi 2 star, then psi 2 star H1 psi 1 d tau, then again A2t will be outside, psi 2 star H1 psi 2 t d tau, and then IH cross del A1 t we have del t, again psi 1 psi 2 star d tau plus IH cross del A2 t divided by del t psi 2 star d tau. And obviously, why it is in red, you know that it will become 0. Okay, and then instead of psi 2, you can write psi 2 a coordinate dependent part and e exponential raised to the power minus E2 t h cross time dependent part. Okay, so this could be replaced, and then what you get is a little rearrangement, and what you get is this one. Again, you know why it is in color, because it's again a normalization condition, and rest of the thing is remains same. A1 t psi 2 star H1 psi 1 d tau, A2 t psi 2 star H1 psi 2 d tau. This 0 goes, is equal to IH cross exponential. Now this exponential part I have brought here, minus I E2 t divided by h cross del A2 divided by del t, and then integral of psi 2 star d tau. So this will psi 2 star d tau will be equal to 1, and you will have A1 t exponential. See this term exponential. This exponential term I have brought on the left hand side. So it will be 1 by this one, and so it is a positive sign here. Exponential I E2 t h cross, and then psi 2 H1 psi 1 d tau. A2 t, again this exponential is on the left hand side, so it will be plus I E2 t divided by h cross and psi 2 H1 psi 2 d tau. And here I have kept intact value IH cross and del A2 t divided by dt. Okay, that's simple mathematics and simple algebra which we are doing. There is no issue. Now the right hand side is on the left hand side is on the right hand side. That's all in this equation. Now if this equation, if psi 1 t is equal to psi 1 exponential minus I E1 t h, and if psi 2 t is equal to psi 2 e minus E2 t divided by h cross, then you can put these values here, and what do you get? IH cross del A2 divided by del t remains same. Okay, A1 t remains same, this part remains same, then psi 2 star H1, and then this psi 1 becomes psi 1 exponential. Again, this equation is very important because psi 1 t or psi 2 t has two parts. One is coordinate dependence, another is time dependence. So this part is coordinate dependent, this part is time dependent. So same thing for the psi 2 also. We have replaced this psi 2 of this integral by this equation, and if you rearrange them, what do you get? Left hand side does not changes, a1t exponential minus this exponential, and now you have exponential minus a1. So you bring this outside, and what will happen? This you will see psi 2 star psi 1 d tau will be there, and then again a2t, this exponential is there, and again bring this minus sign. So look at these exponential parts and these exponential parts, and it will become okay like this one. So what do you have? a2t psi 2 star h1 psi 1 d tau, and then psi 2 h1 psi 1 d tau, and then again this also I should have omitted. Okay, this also will go because here this has gone, exponential I e to t divided by h cross, exponential minus I e to t divided by h cross, so it will be exponential as to the power 0 will be equal to 1, but here this you cannot omit because here you have e1 and here you have e2. Okay, so this part will remain, and now you have psi 2 h1 psi 1 d tau. So this is it. If you put these values, a1t exponential is this term, so exponential minus I e2 minus e1 divided by h cross, and then you have this integral psi 2 h prime psi 1 d tau a2t psi 2 star h prime h1 psi 2 d tau. Okay, so this integral will remain intact because of e2 and e1. This integral, this exponential will go because at both the places you have e2. Okay, so this we can write. If we further a1t minus e1 minus e2, so it will be, so a negative sign is there. Now it was e, and now with a negative sign, so e1 minus e2 I have done knowingly. Let's see, this you get. Now you suppose after getting this one that the system initially is in a state 1, and so the coefficients we will suppose a1 naught is equal to 1, and if the system initially is in a state 1, so in a state 2 there is nothing, so a2 contribution of psi 2 should be 0, so psi 2 naught consider as 0 at time t is equal to 0, because initially this time is this 0 is for time, this 0 is for time. So that initially the system is in the psi 1 state and radiation falls on the system, and the moment radiation falls on the system, perturbation begins, and that is time t is equal to 0. So at time t is equal to 0, the coefficient a1 is 0 and coefficient a1 is 1 and a coefficient a2 is 0. Okay, if you suppose this one, then what we say, since h1 is a very small quantity, so a1t and a2t are not expected to differ appreciably from their initial values. So even after perturbation, these coefficients are not expected to be very much because perturbation itself is a very small quantity. So as an approximation, we replace a1t and a2t with their initial values. So if you replace the initial values, what happens? a1 becomes equal to 1 and a2 becomes equal to 0. So the equation changes to IH cross del a2t divided by del t. In the left hand side it remains same. Then a1t becomes equal to 1. So a1t is 1. Then exponential minus e1 minus e2 divided by h cross remains same. Psi 2 star h1 psi 1 d tau, and then a2t becomes 0. So the last term becomes 0. Last term is gone. Okay. So finally you get this particular equation after the introducing the time dependent perturbation on the molecule. Now what happens that if we take the electric field of the radiation which is falling on the system only in the z direction for convenience, then your h1 becomes equal to, means perturbation becomes equal to minus mu z E naught z divided by 2 exponential I omega t minus exponential minus I omega t. And if you put this value of h1 into the previous equation, mu z is the z component of the dipole moment. So this is a z component of the dipole moment, and E naught z is the z component of electric field. So if you substitute this value in the above expression, what do you get? You see, psi 2 h prime h naught you were having. Previous equation is this one. Psi 2, you have h1 here. So after getting this equation, we are looking at the perturbation terms, and the perturbation terms is this one now. Minus mu z e naught z divided by 2 exponential I omega t minus e exponential minus I omega t psi 1 d tau. Okay. So we have the exponential terms and we have the constant terms. So you can bring these constant terms outside the integral, and if you bring this outside the integral, then IH cross comes from left hand side and you have minus E naught Z to IH cross, and mu Z I have kept here knowingly. Mu Z I have kept here knowingly. Okay, then you have exponential term E I omega t minus E exponential minus I omega t, and if you combine these two exponentials, then what do you get is this one, the same combination, nothing else. Okay, this minus this. Now finally the combination will give you this one. Okay, now the integral which I have kept here, this integral mu 2 star psi 2 star mu z psi 1 is actually transition moment integral. Transition moment integral. Okay. Before going to this time dependent perturbation, you please go and see the modules of particle in a one-dimensional box, where I talked about transition between the energy levels in particle in a one-dimensional box, and you will come to know that I said you that this transition moment integral should not be equal to 0 for the transition to take place. Okay, so this particular transition moment integral is given a symbol mu z 1 2. This I have written as mu z 1 2 in the next equation. Okay, so this mu z 1 2 is transition moment integral. Rest of the term was same. Now exponential terms also I have brought here, omega t. So you get this particular equation. Now you see del a2 divided by t divided by del t, it is there. So it will give you if you integrate, it will give you a2 value. And what is a2 value? A2 value is the coefficient of the second state, second energy level. Okay, so this will tell you if you want to get the probability that whether the system is in the second energy state or not, then what do? You multiply a2 star into a2, and this gives you the probability. Okay, so from this you can find out the probability, and that probability depends on transition moment integral. So if this is equal to 0, transition moment integral is 0, then this probability will also be 0. Means no transition will take place. That's why we say the transition moment integral must be non-zero for a transition to take place. If it is 0, transition will not take place. Okay, so that I use the statement. Now you have in time dependent perturbation theory a proof of this. Okay, where psi 2 star psi 2 psi 1 d tau is equal to z component of the transition dipole moment between state 1 and state 2. Okay, so if this is equal to 0, then this becomes 0 and there will be no transition. This principle we talked about, but why is it so that there will be no transition if transition moment integral is 0? It's now clear from the time dependent perturbation theory. Okay, transition occurs only between states for which transition moment is non-zero. Okay, integrating above equation between time 0 and t gives you this equation. If you integrate this equation, the first equation, this equation, then you get this equation, and since we have assumed A2 is greater than E1, A2 is greater than E1, so the second term or RHS will be dominant. Okay, because see A2 is greater than E1, so the second term will be dominant term. This term will not be dominant, and so we will keep that only. And what does it gives you in the denominator? If you look at that, it gives you E2 minus E1 minus h cross omega. So if you write E2 minus E1 is approximately equal to h omega, then E2 minus E1 is equal to h nu, and this is the principle which we got in Bohr's model. that when the transition takes place from one energy state to another energy state, then the transition delta E is equal to h nu. So this we have done in Bohr's model. Now we are getting in this equation also, E2 minus E1 minus h cross omega. Okay. So the denominator of this equation gives you the Bohr's frequency, and the probability of absorption of radiation is proportional to the probability of the molecule being present in a state 2, which is given by A2 star into A2. I said you that A2 star into A2 you will do, and if this will become 0 when you have transition moment integral is equal to 0. So this A2 will be 0 and probability will be 0. So transition moment integral has to be non-zero. And if you plot this probability, then what do you find? Represent the probability that 1 to 2 transition at a frequency omega is equal to 0. At 0 value, you have a maxima. And if it has to be equal to 0, then E2 minus E1 will be equal to h cross omega, and this will be equal to h nu, which is the Bohr's frequency condition. So from the time dependent Schrodinger wave equation, using the time dependent Schrodinger wave equation in time dependent perturbation, what we got a relationship which relates transition moment integral to the probability of finding the system in higher energy state when electromagnetic radiation falls on the molecule. Means it tells you that whether the transition is feasible or not feasible. And it also gives you a conclusion which was well known to you from your +2 standard, that whenever transition takes place in the hydrogen atom, the energy which is absorbed or emitted is equal to delta E, difference between the energy level. So that we got A2 minus E1 is equal to h nu. Bohr's frequency condition we got, and what we got was a relationship with which we can now be sure of it, the transition moment integral must be non-zero for a transition to take place. Okay, this is the principle which I told you in the particle in a one-dimensional box, where I have proved it with the time-dependent perturbation. Okay, so that finishes perturbation part. I think we talked about the non-degenerate perturbation theory, we talked about degenerate perturbation theory, and now a brief introduction to time-dependent perturbation theory also. So all this I did mostly from the Macurie quantum chemistry. I'm writing the reference also. The diagram also you will get in the Macurie quantum chemistry. So you read it thoroughly. That's a very wonderful book, or you consult any other book. But I have given you everything in these slides. Okay, we will not do problems based on time dependent perturbation and degenerate perturbation theory because of the time constraints, and I will see that I'm able to cover as many topics as possible in the quantum chemistry in the next module. Okay, thank you.